Hello friends, welcome to my channel. Let's have a look at a newly appeared problem. Problem 2594. Minimum time to repair cars. In this video, we are going to explain a solution based on binary search and demonstrate the use of binary search paradigm. This problem asks us that given an integer array called racks, representing the racks of some mechanics. Racks I is the rack of the ith mechanic. So this sentence is very important. A mechanic with rack R can repair n cars in R times n squared minutes. So we are also given an integer cars representing the total number of cars waiting in the garage to be repaired. So return the minimum time taken to repair all the cars. So here is another important sentence. All the mechanics can repair the cars simultaneously. So this is the main problem statement. Here we mention that there are two things that are important. For example, this one. A mechanic with rank R can repair n cars in R times n squared minutes. Secondly, all the mechanics can repair the cars simultaneously. So that's the main statement. So here are several examples. So in the first example, the output is 16. So here is an explanation. And in example 2, so the output is 15. So you can go over the explanation. Here the constraints are the following. First, the list racks has a length bounded below by 1 and bounded above by 10 to the power 5, both ends inclusive. So this is basically on the problem size. Secondly, racks I, or the elements in the list, are in between 1 and 100, both ends inclusive. The third one is on the still related to the problem size. The number of cars is in between 1 and 10 to the power 6. So with that said, actually we can do the analysis. So for this problem, here the hint is very suggestive, especially hint 2. So try use binary search. So we are going to use binary search in this example. So here the procedure is the following. First, we are going to define a Boolean function to produce order or monotonicity. So here I'm going to name this function as canFinish. So the argument passed is t. So it represents time. So we're going to return true if the cars can be repaired in t minutes or within time t. So secondly, we want to transform the problem to be that find the minimum t such that canFinish t is true, right? So here the observations or the key observation is the following. So a mechanic with a rack R can repair n cars in this minutes. This is R times n squared. So this sentence indicates that the smaller the R value, the higher the mechanic's efficiency. So as such, we can sort the list racks increasingly so that we can first look at the mechanics with high frequency, in other words, low R values, in order to accelerate the Boolean function canFinish. So this point will be clear if you see the canFinish function. Then the rest is standard binary search paradigm. So you can search the channel name, say Code-Yao. So for more practices for such problems. So next we're going to implement the procedure. So as a preparation, let's call it step 0. So I'm going to do the sort. We're going to sort the racks from small to large. So here we can do the sort in place. Then this step, or the merit of this step, will be clear. So essentially, you do not need to use sort, But if we do the sort, actually it seems sometime in the can finish function, but you also need to notice that the sort is an O(n) logarithm n time complexity algorithm, right? So let's first make this here, and then we do the following steps. Step 1. So we want to write a Boolean function to produce monotonicity, so that we can do binary search. So here I'm going to define can finish like this. So given a minute t. So we want to check if we can finish all the cars in the given minutes. So first, let's initialize a result which counts, right? So the initially is 0. Then we're going to iterate for r in rex, right? So we want to check for the current mechanics how many cars he can or she can repair within t minutes. So this is nothing but increment this one. So we're going to do t over r, then take square root. So you can do this math square root, or just to the power 0.5, right? So you can do this. So here actually you can do integer division, right? Because we want full squares. Then we're going to take the integer part for this. So here we can insert a early stopping or early return statement. If result is larger than or equal to a number of cars, it means that we can finish, so we can return true. So after the for loop, if nothing has returned, we just return false. So this is the Boolean function, which is actually very straightforward. Basically, once the rex, the list is fixed, so this is a linear algorithm, right? And then what we're going to do is to do the binary search. Step 2, binary search. So here are 3 ingredients. First is the search range, right? And secondly is a shrinkage pattern. Thirdly is the proper return. For this, because we need a positive time, so the low of the time, I'm going to set it to be 1, right? And the high, so let's use the lowest efficiency mechanic to finish all the cars. The time taking is nothing but rex -1, because this rank is already sorted, so that rex -1 is the largest one. Then times cars square, right? Cars square due to here, right? So this is a search range. Basically, let me put some annotation. This is a search range. Next, we want to do the while loop. This is the standard. So low less than high. So notice that here I'm using strictly less. So then we're going to do a shrinkage mid. So I'm going to do this. So high minus low. So this is the base. Starting from there, we're going to go up. This is the increment. So this is the shrinkage. The search range shrinkage. And then we're going to check the function can finish. If can finish mid, it means that if we use this number of minutes, then we can finish all the car. Then we want to try to search smaller ones. So we're going to set high to be mid. Notice that this is also important. We set high to be mid, because mid is give a true value for this Boolean function, right? Secondly, otherwise, so we're going to means that mid is too small. We cannot finish. So we're going to set low equals high plus 1. Not high plus 1. Mid plus 1. So this is the other end. So afterwards, so we're going to do the return. Because of the way we write the binary search, so the high always makes this can finish true. So we're going to return high. So this is the a solution format to this problem. So before we do anything, let's first make a test or check. Yeah, it passes the first example. Now let's look at generic case. Yeah, it passes all the cases. Here, let me make several comments. First, I want to do a time complexity analysis. So here, what we are doing actually is the main thing is the binary search, right? So binary search is a logarithm thing if given the search range. So here, this is low, this is the high. So basically, what we are doing is that the length of this search range is nothing but high minus low. Then we do logarithm. So you can interpret this logarithm as log2, this number of binary search, right? So for binary search, it's O of n, right? Thus, the list has sorted. So, but in this format, we used sort. So basically, sort is O n logarithm n, right? But for this part, low and high, what's it? So log, so high is the max of this rex. So it's basically not the this is not precise. So also we need cars square, right? So this is but high is bounded by this number, the max of the rex. So times cars square. But low is one. We just drop that. So this is the one. But the max is bounded by this one, 100, right? So this is bounded up to a constant by logarithm 100 times cars. Cars is bounded by this number, right? Let's keep that basically cars square. Then up to a constant, basically this is 2 times logarithm the number of cars. So and then basically this number log cars times on plus on log n. So this is the full time complexity analysis for this code. However, if you do not do sorting, it's also okay. Let's copy this part, and then I'm going to change this one to be v1, and then we're going to drop this one because we do not use sorting. So let's comment this out, and then so here we need to change, right? Change to be max rex. So still we can check. But in this second version, what we are doing, we didn't use sort, and here this one we're going to check the full list if there's no early return. And still, what we are doing is that we do this roughly this number of binary search. In other words, call this number of times to call this Boolean function. So the Boolean function is on. Therefore, we have this is the time complexity. Then due to this analysis, roughly this is log cars, and then basically it's log cars times on, right? So the cars is basically this number. You take logarithm, it's 6 times bounded by 6 times log 10, essentially a constant, and then you have on. So basically, it's actually very efficient. So with that said, I guess that's about it for this video. And if you are interested, you're welcome to check out my channel to practice more such problems using binary search. And also you can see other problems. With that said, thank you.